Good morning, Astronomy 1010. Welcome to our sixth lecture, a continuation of our lecture on light and atoms, radiation. Today we're going to have our typical lecture where we'll continue to talk about light and radiation, and then it's going to be followed up with a very special exam review session. This is a very important homework session where we're not going to be working on a homework assignment that's due, but what we'll be doing is we'll be running through some practice problems very similar to the ones you'll experience on the exam. So the session at 1 today is going to be extremely important to prepare you for the test, to give you a sense of the types of questions that I'm going to be asking you, but also to give you a sense of if you can handle them and if you can do them at home without my help. That's going to be a big unknown until we try them. I'd like to make a couple of announcements. Obviously, the exam is next Monday. We've got to take that serious. The multiple choice test you'll take over Blackboard, but my strategy is for us to all sort of log in together. I'll probably click my video off, but I'll be doing things around the house. And everyone will kind of be logged in and they'll be muted and they'll be working on the exam. If you run into trouble, if you need a hint, or if you are unsure what a question's asking, you'll be able to unmute yourself and call me, and I'll be able to kind of address your question in front of everyone. Ava, I might give you extra time. Put it this way. What's timed, Ava, is my participation. I'm not going to sit around for 4 hours, you know. Well, maybe 4 hours, but I won't be doing more than that. I'll log in from 11:30 to maybe 1, maybe 2, if I'm feeling generous. And you'll be able to get some help from me then. But if you want to take, you know, there are people who will just, if you give them an unlimited amount of time, they will just take an unlimited amount of time on the test. And that can be a little troubling, right? I suppose at some point you're just going to get hungry and you're going to need to stop. So Ava, it might not be timed, but I'll need you to get it done that day. Does that make sense? Yes, if you would like to do it at night, you can. But Ava, if you're used to coming, you usually join us during the day class. I would say you should take it at 11:30. That's when your brain is freshest and you'll be best able to take the exam. I would strongly recommend that if you can take it at 11:30, like so many studies show that your brain is most productive and is most awake at 11:30. So I think that's a better time to take it. However, the night students will be taking it at night. So I'll probably log back in to answer any of their questions at night as well. I'm not really sure how this is going to work because I haven't given an exam yet during the fall semester. So this is going to be a little bit of an experiment, but I will be there to sort of answer questions and help, at least during the day, and I will be for a little bit at night.
Okay, Brendan.
Yeah.
This is Bella. So I'm going to ask, are we going to log in through Blackboard or is it Zoom and then or both? Kind
of both, right? So we'll have our normal Zoom meeting. It's just that it'll be kind of silent until someone has a question. You know, during, Bella, as you know from taking my class in person, during the exam, I kind of walk around and answer people's questions. Since I can't walk into your house, I can be here, and if you have questions, I can answer them in front of the whole class and everyone will benefit from the hint. Does that make sense?
Okay. Yes. No, I just wanted to make sure because like I know like you're saying we have to log in through Blackboard for the exam itself. So I wasn't sure if you're doing
you'll just have to have 2 windows
as well.
You'll have a window for Blackboard and you'll have a window for Zoom.
Yep, that's fine.
And for the most part, you won't need the Zoom until you do need it, and then I'd like to be here to help. Okay?
Okay. Yep.
Okay, cool. All right, so another thing that I wanted to announce, let me put this thing down, it's starting to remind me. You guys got my email about the general amnesty, right? Yes, Ava, but I'll go over the format at the end of class today, so stay tuned for that. I have decided to allow the slackers, and let me tell you, there's some slackers out there, to turn in late homeworks and late labs only for this week. And my idea is that'll motivate you to study for the test by going over old homeworks and old labs, especially old homeworks. Actually, some of the labs can be helpful too for the exam. So that's not going to be an unlimited time offer. I'm going to close that out this weekend. So if I were you, I would take advantage of that if you're missing homeworks or labs, and I would get that in. All right. I'm sure I'm going to regret doing this because it's going to mean tons and tons of work for me. So I probably will not be doing this at the end of the semester. This is your kind of get out of jail free card to fix the mistakes you've made at the beginning of the semester. And then going forward, we're going to be back on the plan where we turn it in at the end of every week. No cuts, no butts, no coconuts. But this will help you get motivated to study for the test. Okay. So if you didn't get that email, please be aware of that, that opportunity. We've done up to homework 5 and lab 5. That's right. And this week we did not have class on Monday, so we do not have a lab. And we're not going to have a homework today because we're going to be doing exam prep. That's much more important than a homework. However, today's lecture is testable. So let's talk a little bit about light, and we'll get back to the exam a little later on. I have in my hands here an incandescent light source. You probably can't see it through your camera there, but there's a hot glowing filament that's inside of this bulb, and it's generating some white light. I attempted to collimate the beam of light by cutting a little thin slot into this cardboard, and I was trying to recreate a famous experiment that Newton did. Newton took a light source and he collimated it into a pencil-thin beam, and then he passed it through one of these things. It's a prism. It's just a triangular piece of glass. And I do this demo all the time in classrooms, but thus far, I can't say I've put that much work into it, but I haven't really figured out how to make it work over Zoom, because what you need to do is you need to hit the light against the prism at just the right angle. And if you do it properly, you can make a rainbow. I was going to see if I could make a rainbow that would shine into the lens of the camera, but the angles are not exactly straight. It's a little goofy. I almost succeeded in doing it on the board while I was waiting for class to begin. I had just gotten the beginning of the rainbow, and I don't know if you guys can see that, but you can see blue on one side and red on the other. But the problem is the light source is too dim to collapse it into a bright rainbow. The reason it works well in the classroom is because the bulb I have is 400 watts. This bulb is only 100 watts. Plus, I'm looking through the camera. Actually, I can reproduce it a little more successfully by using something different than a prism. I can use something called a diffraction grating. And let me show you how this works here. I have a diffraction grating over here. Bear with me, students. I did have a diffraction grating. What did I do with that thing? Okay. Oh, here it is. A diffraction grating is a thin piece of plastic that works somewhat similar to a prism in that it creates a dispersion. A dispersion is when you take light and you separate it into its component colors or separate it into its component wavelengths. So what I'm going to do here is I'm going to put this diffraction grating up. And unfortunately, it's not making one rainbow, but it's making multiple rainbows. This is pretty trippy here. But you guys can see that when I pass the white light through the diffraction grating in a number of different directions, I'm separating the light into some kind of component rainbow. I would have preferred to do this demo with the prism and just show you one rainbow instead of 100, but I guess this is more trippy, okay? There are many different devices that you can use to separate light into its component wavelengths. The diffraction grating is one of them. Okay. prism is another. Let me get my lights up here. We're going to take some notes. I'd also like to show you a cartoon of what's going on there. Oops. Let's see here. So here's the idea. Newton took a beam of pencil-thin white light. He struck it at the right angle against a piece of glass called a prism, and he found that he could separate the white light into a rainbow. And he wrestled with what was going on there, but he eventually concluded that the beam of white light contained all of the different colors, and that what he was doing was breaking the white light apart into its component colors. You call it the rainbow, but from now on, we're going to call it the visible continuous spectrum. And not only are we separating light by color, we're also separating it by wavelength, which is kind of the same thing, okay? Let me take a few notes on this since my demo wasn't so great. So Newton used a prism and used the prism to break white light into a rainbow. In doing so, he took what is effectively the first spectrum. And a spectrum is when you break light apart. It doesn't have to be white light, but in Newton's case, it was white light. It's when you break light apart into its component. And here I could say a number of different things. I could say component colors. I could say component wavelengths. I could say component frequencies. And I could even say component energies. It's going to turn out that all of these things are different ways of saying the same thing. They're all related to each other. So color, wavelength, frequency, and energy are all different aspects of the same thing. In other words, for every color, there is a unique wavelength, a unique frequency, and a unique energy. And when you take a spectrum, when you break light apart into its component color, wavelength, frequency, energy, you are doing an art known as spectroscopy. Spectroscopy is the art of analyzing light to learn about the matter that created it. So in spectroscopy, you analyze light to sort of I'm going to keep this simple. You analyze light to understand the matter that generated that light. Well, I had a cup of coffee. Where was that thing? Sorry, guys, I'm not going to get too far today without my caffeine juice. Has everyone written this down? I need to do some erasing.
I'm all set.
Okay, Ava needs a second. Ava, you let me know when you're done. Okay. One of the ways we know that wavelength, frequency, and energy are related to each other is because we have formulas that relate them to each other. You'll remember that in our last lecture, at the end, when you were sort of tired, I introduced several different properties of light. And the properties, now light has many properties, but some of the key properties of light were wavelength, frequency, and energy. And they were related to each other by some key formulas. The first formula was the speed of light is wavelength times the frequency. The second formula was that the energy of the photon is Planck's constant times the frequency. And the third formula, the energy of a photon is Planck's constant times the speed of light over wavelength. Since C is a constant and H is a constant, then these variables are always being related to each other. The variables are wavelength, frequency, and energy. So I've underlined the variables that change here, right? This frequency specifies that wavelength. That wavelength specifies that energy, so forth and so on. We'll try a couple more example problems with this, since I might make you do that on the exam as well. First of all, did we define light? What is light? What do you remember from our lecture last time? Wow. I guess you'd better look it up then, since you can't remember.
Light is made of photons.
Okay, we could start by saying that. I guess I don't want to bust out my super vocab here, but comprised of photons. Okay, yep. Andrew?
It's an electric magnetic wave.
We say an electromagnetic wave, but that's okay.
No, all right.
And as Matt points out, it's comprised of photons. You can think of photons as like particles of light or little packets of light. We don't like to say particle because it turns out that photons have wave-like properties. We'd say it's like a packet, a particle slash wave. Well, we can say comprised of tiny particles, but it turns out, Ava, that not all photons are tiny. For instance, radio photons can be the length of a jumbo jet or a school bus. Another issue is that there is a difference. Well, historically, there's a difference between particles and waves. I wonder if you guys know the difference. Can anyone out there imagine or explain what the difference is between a particle and a wave? I'm guessing that's not something that you guys are going to instantly know the difference. I could be wrong. I need to hide the trolls here because there's nothing fun to look at when you're a troll.
Is the wave constantly moving and the particles more static?
Juan, both particles and waves travel at some velocity. So that's not good enough because both waves travel and particles travel. The difference has to do with something that we call in physics the superposition principle. But I don't want to bust out my $10 vocab just yet. Let's keep it simple. These are particles. See my little moon balls here? These are particles. And particles can travel, Juan, but one thing that makes particles particle-y is they tend to kind of bounce off each other and they go to different places. So this is the stuff that is the blue particle, and this is the stuff that's the red particle, and they don't really get mixed up. Waves are different because waves can overlap one another. Now, I've got a really cool demo that I love to do in my class where I generate some waves, but I need an assistant to do it, and I don't have an assistant here. It's just me. Also, your screen is kind of limited, right? But when you send waves down a string, you're sending vibrations and oscillations, and those vibrations and oscillations can overlap with one another. Maybe since I don't have an assistant here, I can sort of show you in slideshow form. I'm kind of jumping all over the place here today. I know there's a bunch of things I want to talk about, and I'm having trouble figuring out what order. Let's talk about something called interference. Interference is a distinctly wave-like phenomenon. Particles don't do this. Okay, so here's how the demo would have gone if we had done it in our classroom. Obviously, it would have been a lot more exciting to see it in person. I stand on one side of the room and I hold the slinky, and I pick a shy, unwilling to participate assistant, and I make them stand at the other end of the classroom, and they hold the other end of the slinky. And then I start to generate some waves. So what I do is I whip my hand up and down and I generate a pulse, and this pulse is a crest because it goes up. And what you would see happen is that the crest would travel along the string towards my confederate here. And when it hit their hand, it would bounce off of their hand and it would come back as a trough. That's one of the interesting things. If you bounce a wave off of a wall, it kind of inverts. Okay, now the wave that is a trough starts to head back towards me, the professor. But while the wave is heading back, I whip my hand again and I generate a second pulse. And now this crest starts to head towards that trough. What happens at the moment the two overlap each other? They superimpose. The crest, which is like a positive, collides with the trough, which is a negative, and they destroy each other for a split second in time. When they overlap, they cancel each other out. And then, as if by magic, the trough and the crest separate and they carry on their merry way. This is called destructive interference. On the other hand, I could get the friend in the classroom to generate their own pulse, and when a crest meets another crest, they temporarily superimpose to make an even bigger crest. This is what makes waves wavy-like. Waves can overlap each other, and they can add and they can subtract, almost like numbers on a number line. They also do other things that aren't particle-like. Waves propagate through a medium, such as a string or a spring. So if you think about how that differs from particles, I can't give you a particle and I can't take this particle. And if we throw them at each other, the particles don't mush together and overlap to make a bigger moonball, right? They just bounce off each other like stupids. And that's what's the distinction between a particle and a wave. These things are stupid and waves are ghost-like and they can kind of overlap. For hundreds of years, physicists believe that some things were particles and some things were waves, and neither the twain should meet. And then came the 20th century and Niels Bohr and Heisenberg and quantum mechanics and Einstein, and suddenly all of those ideas got mixed up. In particular, what really screwed us up was the concept of the photon. Whereas Ava wanted to call it a particle, it turns out that photons had behavior that was sometimes particle-like. Photons can literally bounce off your forehead and scatter around the room, just like this ball can bounce off my forehead. But then photons also have wave-like nature, and they can overlap and interfere with each other. So what the hell are we supposed to do? Is it a particle or is it a wave? People formed into two camps, and they fought each other for years. And then one day someone said, fuck it, I guess they're kind of like particles and waves, and we have to live with it. And thus was born wave-particle duality. The idea that some things in nature, and by the way, it turns out to be kind of like everything in nature, but I'll get to that later. Some things in nature behave as particles and waves, sort of at the same time. So when Ava said, could we call the photons little particles? I got nervous on two fronts. One, they're not merely particles, they're also waves, and they have wave-like properties, Ava. Secondly, they're not always little. Allow me to introduce you to a friend of mine. It's the totality of all the different types of light that exist in nature, and it is known as the electromagnetic spectrum. You guys can think of it as a continuation of Newton's rainbow, but extended beyond the bounds of what the eye can see. In the middle of the electromagnetic spectrum, we have a pitifully narrow band of light known as the visible regime or the optical regime. This is light that your eyeballs can detect. Your eyeball is sensitive to electromagnetic waves that go from 400 nanometer wavelength, which you call purple, all the way up to 700 nanometer wavelength, which you call red. But there are photons whose wavelength goes beyond red. If we increase the length of our wavelengths into the micrometer spectrum, we discover there's a band called infrared waves, which basically your remote controls and your televisions use. At even longer wavelengths, there are radio waves, which our cell phones use to communicate with radio towers, which radio stations use when we're driving in our car. At shorter wavelengths, there are high energy ultraviolet photons, which give you a sunburn at the beach. There are even shorter wavelength X-rays, which bounce off your bones in medical imaging. And then there are the extremely deadly gamma rays, which mutate your DNA and turn you into a teenage mutant ninja turtle, or maybe the Hulk or something like that, okay? And all of this different stuff is all light. The only thing that makes one type of light different from another is its wavelength. Let's take this as a note because I kind of feel like it's a big deal, okay? So first we have the rainbow. The rainbow is a small portion of the electromagnetic spectrum. Our new term for rainbow is going to be the visible continuous spectrum, okay? The visible continuous spectrum. And when you break light apart into its component wavelengths, unfortunately, my demo failed today, as it has every time I've tried to do it in my lecture here. When you break light apart into the visible continuous spectrum, you get one of two orders of colors. Depending on which way you flip the prism, you either get purple on the left, or if you flip the prism upside down, you get red on the left. For some reason, people have tended to remember the names of colors starting with red on the left. And when you do this, it goes red, orange, yellow, green,
Roy G.
blue.
Biv.
Yeah, you know about Roy G. Biv. In Newton's day, blue was reserved for sky blue, and indigo was the color reserved for dark blue. This is almost an indigo, actually. And then, of course, violet. And as someone pointed out, it goes by the acronym Roy G. Biv. That's the one that's most common and the one that most people know for the. By the way, every rainbow always preserves this order of the colors: red, orange, yellow, green, blue, indigo, violet. The one thing that's weird about Roy G. Biv, if you ask me, wow. Hello?
Hello.
That was weird. You guys
Yes.
just suddenly disappeared. Any thoughts about what happened there?
Lost internet connection for a second.
I guess. I hope it didn't mess up the recording, that's all. But I think this happened before. All right, let's just give it a second for everyone to get back here. Are there trolls present? I have to look for trolls now. Show none.
Yeah.
Okay, the trolls
Here.
are. Okay, some trolls are here. Thanks, Greg. Thanks, Kelly. All right. They have a quick access button to show trolls, but they don't have a quick access button to hide trolls. And I think that design feature leaves much to be desired. All right, trolls are hidden. All right, sorry about that, guys. Here's the point I was trying to make before I got sideswiped there. Although it's customary, and you'd heard someone shout out in the background before we lost connection, Roy G. Biv, it's legendary, right? What's weird about Roy G. Biv, if you ask me, is that the wavelength of red light is 700 nanometers, and the wavelength of violet light is 400 nanometers. By the way, I'd love to tell you the story of how people eventually connected color to wavelength, but it's involved and it's complicated. By the way, guys, what is wavelength? I just need to know that you understand something about this. What would you say is the definition of wavelength?
It's colors, units.
Wavelength is the same as color, but that's not the definition of wavelength. What's the definition of wavelength? It has to do with a wave, I'll tell you that much. Something about this is related to the concept of wavelength.
Is it the distance between the two crests?
Exactly, Jake. You can think of a wave as a repeating cycle, right? In fact, anything that's cyclical is wave-like. And the wavelength is a real physical measurable distance. As Jake said, it's the distance from crest to crest. And Jake, I would say it's one of the key characteristics of any wave is the length of the wave, okay? I like to organize the rainbow in order of increasing wavelength. Why? Just because I do. I like it when short wavelengths are on the left and long wavelengths are on the right. And in that sense, it might be better to label the visible continuous spectrum as not Roy G. Biv, but violet, indigo, blue, green, yellow, orange, red, or what I like to call VIBGYOR. So in this case, you'll see that I often prefer this order of the colors. Sorry, it's not actually in color. VIBGYOR is the rainbow, or what we call the visible continuous spectrum. However, as I mentioned, the visible continuous spectrum is one small part of the total electromagnetic spectrum. Let's take some notes on the electromagnetic spectrum. Sometimes we refer to them as regimes of the electromagnetic spectrum. Let me get rid of these party lights here. A regime is like a zone or a territory. Let's do it in order of increasing wavelength. I want you guys to take this as a note because it's kind of important. And we're going to measure the wavelength of light in nanometers. And it's going to increase to the right, a la VIBGYOR, not Roy G. Biv, okay? In the center, the types of light that our eyes detect is called the visible spectrum or the visible regime. I should have you know that astronomers often refer to the visible regime as the optical regime, because in the optical regime, you use lenses and things for optics to control the light. That, of course, is VIBGYOR with 700 nanometers on the right, 400 nanometers on the left, okay? Class, what's a nanometer? Can I erase this down here? I'm doing it. Class, what is a nanometer?
Isn't it a thousandth of a meter?
Huh?
A thousandth of a meter?
Nope, that would be a millimeter. A millimeter is a thousandth of a meter. All right, I'm going to give you 3 different units. 1 nanometer, 1 micrometer in 1 millimeter. A millimeter is 1,000th of a meter. Since 10 to the power of 3 is 1,000, 10 to the power of -3 is 1,000th. Do you guys want to guess what a micrometer and a nanometer are? Put on your thinking caps. You can do it. No? That's too much for you, huh? Frank? Frank, what's a nanometer? Gabby knows. You forgot the 10 though, Gabby. 1 times 10 to the power of -9. Here's how if you were going to chat that, Gabby, I'll show you how I would have chatted that. I would have said 10 to the power of -9. Okay, whatever. So Gabby guessed correctly. By the way, what is 10 to the power of -9? How do I say that in English? What is 10 to the power of 9 equal to? I told you this on your first day of lecture.
Oh, I get it. I think I got it.
Would it be billion?
Yeah. Why don't we write this down? Billionth, thousandth. What's a micrometer? This is micro. The universal symbol for micro is the Greek letter mu. Can you tell me what a micrometer is? Can you guess? Come on, it doesn't take a Sherlock Holmes to figure this out.
10 to the -6th.
1 millionth, correct. Nice teamwork there. Okay, now that that's straight, you'll notice that the visible spectrum is in the nanometer range, from 400 to 700 nanometers. After red comes a regime known as the infrared, or IR. Infrareds start off around 1,000 nanometers. Can anyone guess how many micrometers that is? 1,000 nanometers would be how many micrometers? I want you guys to get good at the metric system. That's one of my goals. I want you to think hard. I'm going to turn the heat down in my apartment because I'm overheating. 1,000 nanometers is how many micrometers? Well, what's the answer?
1.
Yeah, 1 micrometer. Very good. So sometimes what we say is that the infrared regime, it starts around 1 micron or 1,000 nanometers, and it goes all the way up to about a millimeter or so. After 1 millimeter, how many micrometers is 1 millimeter? Oh, never mind. You guys are too slow. You guys need some coffee. Okay, after 1 millimeter, we transition to a new regime called the radio regime. Radio photons, as I explained to Ava, are really long photons. A single particle of radio light can be longer than a damned school bus, okay? Your cell phone is a little radio transmitter. And I believe that the typical wavelengths are around a millimeter or so. So cell phones broadcast right around there. On the short end of the spectrum, we first have the ultraviolet or UV portion of the spectrum. That starts around 400 nanometers and it goes down to about 10 nanometers. Then there are two more regimes which are even smaller wavelength. I'm sorry, I didn't really partition this out right, so I'm going to have to compress them. There's the X-ray regime. And X-rays go from 1/100th of a nanometer to 10 nanometers, 0.01 nanometers. And then there's the very short wavelength gamma rays. Gamma rays start at 1/100th of a nanometer and in theory just get smaller and smaller all the way to infinity. Gamma rays are the smallest wavelength light, but they're also the most deadly. And that's because wavelength increases towards the long end of the spectrum, but energy of a photon increases towards the short end of the spectrum. Hey class, if you had the choice of getting irradiated with radio waves or gamma rays, which would you choose? Would you rather be irradiated with radio waves or gamma rays?
Radio.
Yeah. Radio waves are harmless. They pass through your body without disturbing any of your cells. If you go into a room full of gamma ray radiation, you will get radiation sickness and die. That's what happens to people during a nuclear reactor meltdown or during an atomic bomb explosion like Hiroshima or Nagasaki. Those bombs literally flood the entire city with gamma ray light, causing hideous mutations and radiation burns. Gamma rays are dangerous. Radio waves are safe, more or less. Okay, so now you know a little bit about the electromagnetic spectrum. You also know that there's a relationship between wavelength, frequency, and energy. Let's just take a moment to do a sample problem of the type that you might have to do on an exam. Can I erase? That's slide 63 if you need to copy it again. Here's a green laser. I use it for astronomy purposes. You know, what makes a green laser? A laser is a monochromatic source of light. Monochromatic means one single wavelength. Unlike regular white light or other types of green light, this laser produces a very unique beam of photons. Let me show this up close to you here, Logitech Capture. So I'm loading my Logitech program so I can focus this. So when you have a laser, laser light is monochromatic. That means single wavelength, okay? And in the case of my green laser, let's see if we can focus this so you guys can read the fine print. Still a little too close to the camera here. Let's try to focus even more. This is kind of cool. We're going to really zoom in. Can you guys see the wavelength? What's it say?
Is it 532 nanometers?
That's right. It's 532 nanometers, which, as you can tell, is a very green. 532 nanometers is right in the middle of Roy G. Biv. It kind of looks like shit on the camera. Let's see if I can just mess with you guys. Wow. no. Okay, whatever. The CCD camera doesn't like it that much. All right, so if I have a green, by the way, this beam is not made of one photon, but there are bazillions and bazillions and bazillions of green photons that are leaving this laser every second, okay? So even this spot on my hand is a bath of like 10 bazillion, trillion, million, billion photons. But we're gonna just analyze one single photon. So let's say we have one photon of a green laser, has a wavelength of 532 nanometers. Suppose I want to find the frequency and the energy. Do you guys know how to do that? Tell me what to do. I need some formulas, right? Let's start with the frequency. What's the formula? I had you write them down earlier. 1, 2, 3, right? Give me a formula. Could someone please participate with me? I feel very lonely here. I feel like I'm just talking to no one and it's kind of stressing me out.
Would one of the ones be E equals H times F?
That would be helpful to get the energy if we knew the frequency. Yet we've been given the wavelength here, right?
Mm-hmm.
So pick another one, Frank.
Would it be E equals H times C divided by the wavelength?
We can use this. We have the wavelength, Frank. These are known constants, so I can use that to calculate the energy. Would you like to do that first?
Yeah.
Okay. I know that Planck's constant is 7 times 10 to the minus 34 joule seconds. I know that the speed of light is 3 times 10 to the 8 meters per second. What do I do about the wavelength?
I think you would have to you have to like reduce the nanometers to meters.
Yeah, I wouldn't say reduce, I would say convert, because you're not actually changing the length of the wave, you're just changing the units that you measure the wave, right?
Mm-hmm.
Like for instance, Frank, I could measure an ant in meters or I could measure an ant in millimeters, but I'm not reducing the ant. Okay, whatever, just semantics. But very good, Frank. So how do I do that? How do I convert 532 nanometers into meters?
Dimensional analysis, and you would have to, let's see.
So just tell me what to write. Remember, during the test, it's going to be up to you guys to do this by yourself. So Frank, tell me how to do it.
First, write down 532 nanometers.
Correct.
Times that by then nanometers on the bottom and meters on top.
Okay. Now what? So far, so good.
1 nanometer on the bottom.
Yep.
And I
Right in your notes.
You would put 10 to the negative 9 billionth.
Well, no, just say 10 to the minus 9 or 1 billionth, either way.
Oh, okay.
And what does that turn out to be when you multiply the two?
Would that 5.32 to the negative 6th?
Oh, I was worried that you were going to fuck that up, Frank, and you fucked it up good, okay? Let's talk about what you did. I already know what you did there. When you saw 10 to the 9th, I bet you typed it in this way. I bet you typed in 10 exp negative 9, didn't you?
Yeah.
But guess what that is? That's
Mhm.
10 times 10 to the minus 9, which is actually 10 to the minus 8. You see, Frank,
Oh,
that's not 10 exp minus 9. That is 1 times 10 to the minus 9. Also, Frank, you could have made this a lot easier by just doing 532 times 10 to the minus 9 meters. But for the record, that's not 10 to the minus 6. That's 5.32 times 10 to the minus 7. And if you got 10 to the minus 6, that means you botched this part. That's actually a very instructive exercise, Frank. People do that all the time. And it's good that we had this talk, okay? You'll never make that mistake again, will you?
I won't.
Okay. And I hope none of the
Hopefully.
rest of you do either, because I've seen that one before. By the way, I prefer this one to this one, but it's a matter of taste. So let's write that in. Guys, can you calculate the energy for me? Could you punch that up real quick? I'm just waiting for someone to give me the answer. Okay, why don't you read it out to me? 2 sig figs. Just anyone. Just tell me what you got.
3.9 to the negative 19th.
Jake, one more time.
3.9 to the negative 19th.
What are the units? You guys always have to ask yourself what the units are.
Meters?
No, meters.
Meters per second.
Meters
No,
cancel.
it's joules.
It's joules. Seconds cancels with per seconds, and it's an energy, so it's measured in joules. By the way, it's customary to convert that to electron volts. I don't know if I feel like waiting for you guys to do that. Divided by 1.6 exp negative 19. That's about 2.4 electron volts. If you use your conversion from joules to electron volts. Okay, that kind of took too long of a time, so I'm going to skip the frequency part. But those formulas can be used to convert from a wavelength to an energy, as you just saw. All right. So now you know about light, right? Actually, let's try one more problem where we calculate frequency. Let's try a radio wave. How many of you remember WBRU? Well, I guess it still exists, but how many remember WBRU when it was like alt rock and not Christian rock? Any of you? No, or are you too young? God damn it. Well, you know, back in the day, there was a radio station in town that would play Korn or Limp Bizkit or Nirvana or whatever. And that radio station was called WBRU. It was started by some Brown students. Yeah, 95.5. 95.5 what, Enrique? Do you know how you build a radio tower? You just get a conducting pole of metal and you send some electrons into the radio tower. So watch this. You hook it up to a power company and you send the electrons up and down and up and down and up and down, and you oscillate them at a frequency of 95.5 megahertz on your radio dial. That means 95 million cycles per second. And out of your tower comes a huge ass radio wave. The radio wave has a frequency of 95.5 megahertz. Our goal is to determine the wavelength of WBRU. How do I do that, students? This could easily be an exam question. What formula do I want?
You could do wavelength equals C over F.
Correct. Let me just state it for the others who might not have figured out what you did there. He started with the speed of light is wavelength times frequency, and then he solved for the wavelength. Wavelength is the speed of light over the frequency. Now, the speed of light is 3 times 10 to the 8 meters per second. What's the frequency?
You gave it to us.
Yeah, but it's not the right units.
Oh.
What are MKS units of frequency? What the shit is frequency? Does anyone know what frequency is?
Cycles per second.
Yeah, and that's right, Enrique, it's in Hertz. Let me just show you how that works here. I want to make sure that you guys have an intuitive understanding of frequency. I have an animation of a traveling electromagnetic wave. This could be the WBRU photon right here. Except it's not, because it's a little slower. You can see crests and troughs of your wave traveling across the screen. Oh, shoot, that's not what I wanted to do. Let's get a reference point with my annotation tool. And let's have my reference point be right here. Okay. Frequency are the number of cycles or wavelengths that pass by that red arrow in a second. Why don't we count the frequency together starting when this crest hits the arrow? Ready? 1001, 1002, 1003, 1004. Boom. So this wave has a frequency of 1 cycle every 4 seconds, which is 0.25 hertz, 0.25 cycles per second. Here, I did not give you the frequency in hertz. I gave it to you in megahertz. Your job is to convert from megahertz to hertz. How do I do that? Give me units, top and bottom.
Megahertz on the bottom, hertz on top.
Now, do you know the conversion for mega?
Isn't it 1 times 10 to the 6th?
Excellent.
Like-
Where does the 10 to the 6 go?
On top and 1 on the bottom.
Very good. 1 mega is 1,000,000. So I guess that means 95.5 times 10 to the 6. Here I'm going to write my hertz as 1 over seconds for unit reasons. Guys, calculate it to 3 sig figs. I want 3 sig figs. Well,
I got 3.14.
That's what I got.
Units.
Meters.
Is that a random number?
No.
What is that?
pi.
Holy shit, dudes. WBRU broadcasts at a wavelength of pi. Now, do you think that's random? Do you think a bunch of engineering nerds, some hardcore electromagnetic lovers on College Hill in the 1960s started a radio station for students and that it just happened to be broadcasting at pi meters? Was that random?
Yes, completely random.
No, those
Hell no.
Those nerds did that on purpose. They designed their radio station. If they were going to pick a radio wavelength, they were going to broadcast at pi meters. By the way, how big is pi meters? How big is 3 meters?
About 9.5 feet.
Here's 1 meter. Here's 2 meters. Here's 3 meters. I guess I could try to turn my camera up. 3 meters goes all the way up. My ceiling is a little over, my ceiling is about pi meters tall. And I've got some tall ass ceilings.
Yeah, that's Nadia's costume. Oops, sorry.
So that's kind of interesting, right? So Ava, I don't know if you're still in the troll zone, Ava. Ava, is a WBRU photon small? Are photons tiny? Ava? I don't know if she's still with us. Oh no.
She's there.
Ava, are you am I tiny? Okay, you are here, Ava. Photons are not tiny, Ava. Oh, your answer is no, right. Ava, oh, I see, you said yes, I am here. Right, Ava, 3 meters is not a tiny photon, which is why when you said photons are tiny particles of light, I could neither condone particle, nor could I condone tiny, because it made me think WBRU can have photons that are 3 meters long. And that's a really long ass radio photon, all right? Where does light come from? Like, does light just exist, or does something have to make it? I guess there's light that's left over from the Big Bang. That's just sort of there. But most light comes from something. Like in my phone, I can generate light, right? I can use the flashlight app. Where do those photons come from? They're generated inside the microscopic world of atoms. Let's go back to atoms and let's think about that. Joel, I'm glad that you got here for WBRU broadcasting at Pi, because I was worried all these Gen Z kids didn't know what WBRU was, and it was giving me the willies, okay? But apparently...
Well, I don't know what WBRU is either. I didn't grow up down here, so...
Oh, shit. Well, Enrique did. I'm with you, Enrique, okay? All right. So, photons... Sorry, my handwriting is bad today. Photons are formed inside atoms. And the process by which you generate photons is known as emission. Now, you guys learned a little bit about atoms last time, but because I was in a rush, I didn't get to do this little game with you. So I want to do this game now. Let's build a couple of atoms. Let's build an atoms. Sick, okay? In my first, to do this, you're going to need that little part of your notes on atomic number and mass number. In our first atom, we have an atomic number of 1, a mass number of 1, and the atom is electrically neutral. Jake, you're up. Help me build this atom. An atomic number of 1, a mass number of 1, and it's neutral. You can think of this as Basically like training for your exam, because I'm going to ask you these types of questions during the exam.
All right.
So Jake, let's go to your notes, and why don't you regurgitate the definition of atomic number for me?
The number of protons in an atom.
So how many protons does this atom have, Jake?
2.
Wait a minute. You just told me the atomic number was the number of protons in an atom.
1.
Right. Okay, Jake, what does the mass number tell us?
That is the number of nucleons in an atom, so that would be 2.
If this is the number of nucleons in an atom, then it should also be 1, because it says 1, right?
Yep.
So how many neutrons does this atom have?
1.
False again, because you've forgotten what a nucleon is. What's a nucleon? Look in that same section for the definition of a nucleon. Feel free to rescue Jake if you can.
Yeah, lifeline.
A neutron, or no, a nucleon.
Yeah, what's a nucleon?
So a nucleon, you add the protons and the neutrons together to get the number.
It's
of
protons or neutrons, but essentially, yeah. So how many nucleons do I have so far?
1.
1.
This is a nucleon. And the mass number tells us we can only have 1 nucleon. So Jake, how many neutrons are in this atom?
1.
But then I would have 2 nucleons, because a proton is a nucleon and a neutron is a nucleon. Yet
So
this
2.
tells me I only have 1 nucleon. Do you see? Or have I got you totally confused?
I mean, I'm totally confused.
Yes.
So
That's the
Brendan,
point. Yeah.
set it up on the whiteboard this way. So your atomic number plus X, A plus X equals M.
Okay.
So your atomic number is the number of protons. X is the number of neutrons equals the mass number, which is the sum of protons plus neutrons.
Right. So what does X equal?
0.
Exactly. There are
That
0.
makes sense, Jake?
Yeah, that makes sense.
Actually, Joel, nicely done. I like your style there. That was cool.
Because like I knew one of the things was the like product of 2 numbers. I just didn't know what it was.
Well, product means multiply, so we want to say
Well,
sum.
I'm not good at math, so.
All right. What does electrically neutral mean?
Number of protons equals the number of electrons.
So how many electrons does this atom have?
1.
Right.
Thank
This
God.
is probably the most famous. Wait, did you say thank God I got one right? Is that what you said? It's okay, Jake. We have to, this is a learning process. By getting it wrong, you're actually learning more than if you get it right, okay? This
Okay.
is probably the most famous atom in all of nature. It's the only atom that has no neutrons in it. This atom is known as, take it away, class.
Hydrogen.
Water, H2O.
No.
Or no.
Water's a molecule. We'll get to that later. This is hydrogen. This is a particular isotope of hydrogen, a legendary isotope. What's the name of this isotope?
If my brain worked, I would remember it from summer session, but I don't.
That's okay. Probably no one knows this. The name of this isotope is called protium. Hey, Cam, there's a Cam in my 1010 class and a Cam in my 1020 class. I know, pretty wild, right? One of the Cams did not turn in a homework or a lab. And I'm worried that was you, Cam. So I need you to go back while I have my amnesty in place and check for that and make sure you've got all your homeworks and labs turned in. Okay, buddy?
I'm pretty sure I have them alternative, but I'll look though.
It could have been one of those things where you submitted and it was processing. I don't know. Just keep an eyeball on that. I wanted to talk to a Cam. I remember that. Cam, I want you to help me build another atom. This atom has an atomic number of 1, a mass number of 2, and is electrically neutral. Can you help me build that atom?
So
Let's start with your atomic number.
okay.
What does the atomic number tell us?
8. So it'll be 1 plus 2
Wait.
or 2x.
But forget about this shit. Just what is the definition of atomic number?
I know what it is, but I forgot how to describe it.
Well, then just read it off your notes.
Did I write on my notes? I'm pretty sure.
It should be. Jake, you read it a moment ago, right? Jake read it out loud. What was it, Jake? Jake probably knows now because he's been publicly humiliated, and thus he
the
will
number
never
of protons
forget.
in an atom.
All right. So yes, thanks, Kevin. So how many protons does this atom have, Cam?
It would have 2 or 1.
Well,
Don't do what I did. Do not do what I did.
yeah, that's exactly what Jake did. He said the atomic number is the number of protons in an atom, therefore it has 2. But we can see right here that it actually has 1, right?
Right.
Because
So
that's
it's
all right.
1.
It's okay. So 1 proton. What is the
Keep it simple, guys.
What is the well? Simple isn't always as simple as you think it is. That's just the truth. It's funny how that works. What about the mass number? What does that mean?
The mass number is the number of nucleons in an atom.
Okay. So,
So
how many? Yep.
therefore it makes up protons and neutrons.
Yep. So how many?
I'm
Neutrons?
gonna guess 0, right? Or
But-
2.
If there's wait a minute, hold on. If there's 0 neutrons, then you only have 1 nucleon, the proton. But this says you have 2 nucleons.
Oh, then you probably would. Oh yeah, I think it's 1.
1.
1 nucleon.
No, 2 nucleons.
2 nucleons. Okay.
So how many neutrons?
0.
But then I only have 1
It's
nucleon.
1 neutron.
It's
Okay.
1 neutron, right?
All right.
Now I have 2 nucleons. This is a nucleon and this is a nucleon. This tells me how many protons. This tells me how many nucleons. I guess we should do the A plus X thing again, whatever. All right. How many electrons does this atom have?
2.
But a neutron has no charge. If it's neutral, there should be no net charge. 2 electrons is -2. 1 proton is +1. +1 minus 2 is -1. That's not a neutral atom.
Okay.
How many electrons?
So it would be 1, right?
Yeah, that way it stays neutral. What is this atom?
I have that memory of the periodic table.
Well, the number of protons defines your atom. The atomic number. This is Gabby says this is still hydrogen. But Gabby, this is a legendary isotope of hydrogen. Who knows the name of this isotope?
I know.
What is
Helium.
it?
Helium.
No, helium is a different atom. These are the same atom. They're both hydrogen, but they're different isotopes. They're like different flavors of hydrogen.
Would it be deuterium?
Thank you, Frank. Nicely done.
Nice.
This is the most famous isotope in all nature. Well, protium and deuterium are isotopes of each other. Normally, when people say hydrogen, they're referring to protium. When they say this guy, you can think of it as heavy hydrogen. They call it deuterium. You might wonder why sometimes you can have a neutron and sometimes you don't. Ask the Big Bang, okay? The Big Bang did that to us. Let's go and find some stuff that the Big Bang created. Let's take a trip to outer space together. Let's go somewhere cool like the Eagle Nebula. Take a ride on my spaceship. Okay, so I'm out here floating around in the Eagle Nebula. I've never been here before, but it's a cool, groovy place to be. Here's a high resolution, well, or here's a shitty low resolution image. Here's a nice high resolution image of the Eagle Nebula. So I'm flying through the Eagle Nebula on my flying saucer, woo! And I'm floating through all of this gas. Do you guys see all that gas? If you were to scoop up some of that gas and analyze it and say, what is it? You would find that for every 10 atoms that you picked up from space, so you find 10 atoms, you'd find 9 of them were hydrogen and 1 of them was helium. So basically, this is a lot of hydrogen and helium gas, but it's 90% hydrogen. So let's throw the helium away, although helium is kind of a valuable gas these days on Earth, so you could probably mine this for helium and you could earn a lot of money. But whatever. Let's focus on the 9 hydrogen atoms. Suppose you just kept building up and building up and building up hydrogen atoms. You would discover this as you collected hydrogen atoms, that for every 6,000 hydrogens that you picked up, you would find 1. That's okay, Frank. I guess we can't tease you anymore. We would find 1 deuterium. There's 1 deuterium naturally occurring for every 6,000 hydrogens. And this goes by a name in science. It's kind of a big deal. It's known as the cosmic abundance of deuterium. Not only do I find 1 deuterium for every 6,000 hydrogens, but let's talk about molecules. Let's talk about water, because Andrew brought up water for a second. Some of you probably already know this, but water is a molecule. It's 2 hydrogens for 1 oxygen, or H2O. Now, in my glass of water, oh, I guess I drank it all. In my cup of coffee, which is mostly water, most of the molecules are H2O. But you know what? If I could count through water molecules in my cup of coffee, I would quickly discover that 1 out of every 6,000 water molecules was not H2O, but actually HDO, or a version of heavy water. The same abundance, 1 part in 6,000 of deuterium to hydrogen that I find in the Eagle Nebula is the same abundance I find in water molecules on Earth. And you know what that tells me? That tells me, holy shit, those water molecules came from outer space. They came from those same clouds of gas that were once dispersed throughout the galaxy. Studying isotopes is an important art in science because you can learn the history of where water molecules have come from, and you can trace their history back to the Big Bang. People can study isotopes to learn the ages of dinosaur bones, to figure out if some legendary coin is as old as people say it is. You can do all kinds of cool things by studying isotopes. They're different flavors of atom, and they tell you sort of like the history of matter. Okay, let's do one more little module, a module about how hydrogen can generate photons, okay? We'll keep this real quick. I want to talk to you about how the photons are made exactly. So let's start off with a normal hydrogen atom. In a normal hydrogen atom, in protium, we have one proton and we have one electron orbiting around it. But the electron is by default constrained to move at a very particular orbit. It's the orbit that is closest allowed to the proton, and it is known as the ground state. You can think of the ground state of the electron as being something like the default orbit of the electron. When the atom is cold, when the atom is not very energetic, the electron tries to get as close to the proton as it can, and that's the ground state. Quantum mechanics does not allow the electron to orbit any closer to the proton than this. It is possible to energize the atom and to give that electron a little kick. And if you give it a kick, you can get it to jump to a number of different orbits. But the orbits are not sort of infinite. The orbits are pre-prescribed and unique. Sometimes we label the orbits with a number. N equals 1 is the ground state or the default orbit. But there is another orbit the electron can travel on. That orbit, n equals 2, is called the first excited state. And there's another orbit the electron can orbit on. The third orbit, or the n equals 3 state, and the fourth orbit, and so forth and so on. One of the rules about electrons is they can orbit the proton here, they can orbit there, or there, but they cannot orbit in between. A fancy way of saying this is to say the following thing. The orbits of electrons are quantized. That's a fancy word. Quantized. Quantized means discrete or choppy or even pixelated. You could say pixelated. Pixels are quantized. In a normal atom, the electron is constantly jumping around to higher orbits and to lower orbits. While it would be possible to measure the heights of the orbits in distances like nanometers, by the way, I think the ground state has a distance of 0.05 nanometers. That's how close the electron is to the proton. Of course, 0.05 nanometers is a small distance for you because you're a big, clumsy ogre. But to an electron, 0.05 nanometers is a respectable distance, okay? Now, when atoms collide with each other, the electrons can jump to higher orbits. And then once the electron gets tired, the electrons will drop to high orbit from a high orbit to a low orbit. And this is how photons or light is produced. Let's look at a little cartoon. My electron starts off at a high orbit, like the n equals 2 state. It drops down to the n equals 1 state. And when it drops, the energy of the drop will be released in the form of a photon. And this process is called emission, okay? So emission is when an electron drops from high to low orbit and releases a photon. A photon of unique wavelength, frequency, and energy. Let's draw the cartoon here. The electron drops from high to low orbit, and it releases the photon in the form of energy, a single photon. Now, one of the rules of emission is this: the energy of the drop is equal to the energy of the photon. Which, as you saw before, can be related to its wavelength through that formula. We call these photons emission lines. Now I'm going to give you guys a break because our lecture is just about over, but I want to end the class by showing you a picture of some famous emission lines. I'm not going to have time to calculate them with you because I'm out of time, but I'd like to show you some of the famous emission lines that come from hydrogen. At the top of the slide here, you see the different orbits that an electron can have in a hydrogen atom. Level 1 is the ground state. Level 2 is the n equals 2, n equals 3, n equals 4 states. You'll notice that hydrogen produces a legendary red photon known as hydrogen alpha. Do you guys see which transition is responsible for hydrogen alpha? Its wavelength is 656.3 nanometers. Hydrogen alpha is produced when an electron drops from what orbit to what orbit, class, according to my diagram?
Level 3 to level 2.
That's right. So if the electron starts off at orbit 3, they call it sometimes, Jake, the 3 to 2 transition. Okay, Jake, so that you understand me, the blue line is known as hydrogen beta. It's a very characteristic blue photon that comes from hydrogen. What transition is responsible for the hydrogen beta photon?
Orbit 4 to orbit 2.
That's right. The electron can sometimes leapfrog over and jump right from the 4th orbit to the 2nd orbit. How about this one? The purple photon is called hydrogen gamma.
Orbit 5 to orbit 2.
Right. Now, suppose I heated up hydrogen gas. If I took pure hydrogen gas, Jake, and I was to heat it up, the electrons would start jumping all around, and all of these photons would simultaneously be produced. I'd get 3 to 2 emission, 4 to 2 emission, and 5 to 2 emission. What color do you think the hydrogen gas would be if I mixed all 3 of these colors together?
White.
It would not be white. The only way you can create white light, Jake, is if you mix all of the rainbow together. But when you heat up hydrogen, you don't get a complete rainbow. You just get a red photon, a blue photon, and a purple photon. So let's think this through. Red and blue makes what color? Phone a
Oh,
friend.
wait.
What does red and blue become?
Purple.
Pardon?
Purple.
Okay. So what do you get if you mix purple with purple?
Just like a violet, like a deeper purple.
Just so happens, I think I might have burned this out, so I'm a little concerned. But next week, this is hydrogen gas. This tube is full of hydrogen gas. I'm going to try this, guys. I think I might have burned it out. Now it kind of looks bluish on the CCD, but here in my room, this looks very, very purple. I think that crappy camera there is not picking up the purple as well, but this looks wicked purple to me. Do you see that? That light, Jake, if you were to break it apart and analyze it, which, oh, I can actually, oh, don't burn out on me, baby. Let's take the spectroscope. No, let's take the diffraction, hold on. Remember I had that diffraction grating? bloody fudging hell. If this works correctly, guys, I'm going to hold this grating up. And if I hold it in front of that, you should just see the 3 lines, purple, red, and blue. Let's see if we can do it. That's the background lights. Okay, you know what? Maybe I'll save this for next time. Let's try that one more time. Well, unfortunately, this diffraction grating is, oh, there we go. Well, we'll work on it. I think part of the thing is, do you guys see how it's burning out? I'll tell you what, we'll do it next time. I'm gonna have to go to CCRI and get another hydrogen tube if they have one. Okay, let's talk turkey for a second here. We're gonna take a break for about 15 minutes or so, and then we're gonna start to do our exam prep. Guys, when we start the exam prep, I'll tell you the format of the exam and all that stuff, okay? Let's just take a break because I went a little long there. Sound like a plan? All right, I'll see you guys in 15 minutes, maybe 1:20.
You pause real quick.
Hi, students. I apologize for the delay. I got into a phone call with the lab tech and it took a little more than I expected. Here's what we're going to do. We are going to talk about the format of the exam, the chapters for the exam, and then we're going to try some sample problems to see if you guys could handle a potential exam question. These questions will give you a sense of what to expect on the exam. And even if you can't do it by yourself now, by talking through it, it should help you. Let's just check the, okay. Are there still trolls available? Let me just see. Oh, okay. It's quite a few trolls. Let's go ahead and talk hide non-video participants. Let's talk about the format first. All right. So the test, as I mentioned, is going to be roughly 100 questions of multiple choice. But don't get too cocky about that. First of all, there's 5 potential answers each time, A, B, C, D, E. That means you have a 1/5 probability. If you fill in random bubbles, you should be able to get a 20% on your exam just by filling in all C, for instance. So you have a 1 in 5 chance of just guessing the answer correctly. You should be able to score 20 points if you are at random and don't know any astronomy. If you do know astronomy, of course, your grade will improve. The first section is a section on diagrams. In the diagrams section, I will show you a famous picture that we've studied in our lecture, and there will be questions about the multiple parts. What is the name? Number 1 refers to what thing? Number 2 refers to what thing? Number 3 refers to what thing? There's probably going to be 5-ish diagrams. They'll be close to roughly 30 points. Probably 5 pictures times 6 questions, or it might be 6 pictures times 5 questions, something like that. Okay? Study your diagrams. Know your vocabulary terms. After that, there's going to be roughly 30 points worth of general multiple choice questions. These are usually non-mathematical, but they can involve some math. I call it small math. Small math means you do a really quick calculation like 6 times 3 or something like that. Types of questions that you might find in the general multiple choice are asking you about laws of nature. What is Kepler's second law of planetary motion? What is Newton's second law of motion? Things like that. Which observations did Galileo make? Which observations did Tycho Brahe make? What's the difference between a solar and a sidereal day? Those are things that I might ask. The final 40 points, which is what we're going to focus on today, are mathematical applications. These will be identical in many respects to your homework problems. I'll start off by giving you some givens. You'll have some givens, and then you'll have to do some unit conversions, and then you'll have to use some formulas. Did everyone get a copy of the formula sheet so they can practice with that today? If not, you should probably get the formula sheet now.
No,
Sorry, who said no?
Bella.
Bella, I am going to send it to the class through chat right now. File, AS1010 formula sheet, boom. Check the chat window if you don't have your formula sheet. I just sent it to you guys again. You should be able to download that file there. Okay, now you know the format, okay? Ava asked if it will be a timed test. I am going to log in, and I think we should all log in to a live Zoom starting at 11:30, just like we normally do. And I am going to mute myself. I might even mute my video so that I can, I don't know, slobber on a sandwich or just drool on myself, whatever I need to do in the background. But the important thing is, you guys might want to have me around to either ask me for a hint or to ask me if you're confused about a problem or just to ask me anything. And everyone should benefit from those questions as well. So while you could take it on your own, I think we should all log in, mute ourselves, mute our video, and then only chime in when you have a question. Joel's class did this with me in the summer, and it worked out pretty well, right, Joel?
Yeah.
Until
Until my brain fried.
Yeah, one of the classes I actually fell asleep and I nodded off during because it was like 3 hours of doing nothing and I started to nod off, so I missed someone's question. So hopefully that will not happen, okay? If not, I'll put my cell phone on ring and I'll put it right next to my ear so you guys can jolt me out of existence, okay? But I don't think that'll happen. Now, is it a time test? Well, I'd like to get done that day. Joel took a long time to do it and I gave him that time. And I'm willing to give you guys some extra time if you need it. But remember, midterm grades are due Wednesday, so I'd kind of like to wrap this up by Monday night if possible. A couple of the night students I told could finish it Tuesday morning because some of the night students are getting home from work after a long day at work and they've got kids and stuff to do. So I told one student the other day, hey, look, if you want to do half when you get home and half in the morning, that's fine. But I need to get it done by I want these things wrapped up by Tuesday. Y'all know what I mean? Gina does not see the formula sheet in the chat. Does everyone else see the formula sheet in the chat?
Yes.
I sent it to everyone. Okay, Gina, can you send me your email and I'll just try direct emailing it to you?
I was going to say, I also don't see it in the chat.
What the shit is up with that? Are you guys on your phones or something, or are you on a computer?
No, I'm on the computer.
Okay, so I should probably just send it to everyone then.
I don't see it for some reason either.
That's so weird. Blackboard.
Huh.
I don't understand these things, how this happens. This is Astronomy 1010. It's probably going to make me log in. Oh, no, okay. All users. AS1010 midterm formula sheet. Okay, attach file. Choose file. Just a moment.
Did you put it on Blackboard?
No, that would have been smart, Joel, but I'm not smart, so I didn't do that. I should do that. All right. Why don't you guys see if you can click on it now? Hold on. Sent. So whoever that was who didn't see it, do you see it now? Gianna and friends?
Yes, I just got the email. I'm all good.
Okay. Now, does everyone understand what I'm saying about the time of the test? All right. Let's talk about doing some practice problems together, shall we? Oh, by the way, let's talk chapters before I do that.
I can't see the bottom of the screen or the bottom of the board.
So here are the chapters that you can expect from the book. Chapter 2, Chapter 3, Chapter S1, Chapter 4, and Chapter 5, a part of 5. Basically, whatever we talked about in our class, those are the chapters that are going to be covered. Whatever we covered in our lectures or what was covered here. All right, when you're finished copying, we'll begin trying some sample problems. Andrew, let me know when you're good.
I'm good.
Okay, I'm going to erase. Please let me know if I'm forgetting to address a certain question, guys. I'm trying to be comprehensive here. So those of you, I know some of you in the night class like to join the day class, which I think is great. Ava, if you are in the night class, did you hear what I said about maybe doing it at 11:30? The choice is completely up to yours. And you guys are free to just do it at any point during that day. But Ava, I got to tell you, your brain is never going to be as sharp and crispy as it is about an hour after you wake up. So 11:30 is like the key time. It's the most good time to do an exam. Yeah, and also, Ava, it gives you time to stretch it out at night. Whereas if you start it at night when you're kind of tired and then you start getting panicky, it's going to get ugly, you know? So the night students, I've told them they could finish it in the morning if they need to. Okay, this office hours is going to be run a little bit differently than a typical office hour. And the reason why is during a typical office hours, we're just trying to get our problems done. And I start off with the question and I just walk you through how it should be solved. But that's not going to be helpful here at this point. During the test, you're going to have to solve these questions on your own. And you may find that that's a bit more challenging than it was when I was just kind of doing it for you, right? So we need to practice that terror. I need to give you a question. You need to look at your notes and your formula sheet and see if you can solve it or see how much of it you can get done. And then we should talk about how to do it. Do you understand? So I'm going to give you a question and I'm going to give you 5 or more minutes to see how far along you can get. If you want to ask me for a hint, you can, if you're totally stumped. If you want to talk to each other through the Zoom boxes, that's cool too. But the important thing is you try to do it without me at first. Your first question is going to be a lost at sea question. This is a question that will be on the exam. Here's the setup. The givens are, it is the fall equinox. The sun is at an altitude of 65 degrees in the south on the meridian. The universal clock, the universal time reads 2200 hours. Here are your questions. 1, find your latitude. 2, find your longitude. Here's a hint. This is a very important hint. draw a fucking diagram, okay? There's my hint. You need to draw a diagram to solve this problem. Okay, I never said that. Thank God I've got tenure, okay? But I need to burn this into your brain. It's really important that you draw a diagram. What should your diagram look like? Do you guys even know what that diagram would look like?
Isn't it like the half circle one type of thing?
Yes, yes, Juan. So it should look like this, right? And you should put the boat on it. You should also make sure to label north and south. Now your diagram is not done. You need to put the sun on this diagram. Okay, you've got 5 minutes to work on this while I nibble on a sandwich. Just start doing it and see what you can come up with, all right? Oh. Does everybody know what they're doing here? Hey, Gabby, do you know what you're doing?
I found it.
I'm still looking through my notes.
Well, look, guys, if every time you have to look up 1 + 1 = 2, then you will take 17 hours to do this test. What you should be doing is you should put the sun on the diagram. Can someone in the class tell me where the sun should go on this diagram?
The sun should go, the top of it's the zenith.
Yep. What's that altitude?
And then that is
south up how far? Ava?
Oh, it's 12 o'clock. No, that's where the sun is.
It's 22 hours, right?
Whoa, whoa, whoa. This given tells you where the sun is. Could we focus one thing at a time? This tells you where the sun is. Ava said something intelligent. She said south up, 65 degrees. So that's like what?
About 2/3 of the way up to the zenith.
Right. So here we go. The question is, how does that help me?
You subtract 65 from 90.
Very good. Are you
And that
telling me you know the answer, Jake?
35 degrees north.
That Kevin's got it better. 35 plus 65 is 100, right?
Told you I was bad at math.
Okay, so what's your answer to question number 1?
25 degrees.
That
North.
isn't. Oh, how did you know it was north?
I looked at my notes.
Well, fuck, dude, it might not be north in the next example. How do you know if it's north or south?
Because it's telling you.
Pardon?
It's telling you that's on
Oh,
south.
yeah, giving you the south.
It says
It's the
sun.
fall equinox.
The fall equinox is. Well, okay. What is the significance of the fall equinox? That's telling you that the sun is at the celestial equator. That's what that means.
Yes.
So this is your celestial equator.
Yes.
But that helps you determine that 90 degrees minus 65 degrees is equal to 25 degrees. But that doesn't tell you, that's not why it's north or south. How do you know if it's north versus south?
If the sun is 65 degrees in the south, and that's where you're seeing it, that means you're north of the celestial equator.
That's correct. Listen to me now. What Joel said was correct. If the sun is in the south, you were in the north. If the sun is in the north, you were in the south. That's how you know. We put our plants in the south window to get maximum light. But if you lived in Argentina, you'd put your plants in the north window, okay? Now try to find the longitude. What's that, please?
Ava wants you to say it again.
All right. Ava, I will say it again, but I think I should help you with the diagram, okay? Bear with me, buddy. Nope. Nope. What the hell? I am stupid because I didn't get time to eat my sandwich. And that makes me dumb because I have no brain sugar. Okay. Ava, I want you to look at this diagram, Ava. This diagram shows you the path of the sun in our local sky. Slide 22. In a northern observer's position, the sun is always traveling on paths that go through the southern sky. This picture here tries to show you, if you're in the northern hemisphere, the sun is always traveling through the southern part of your sky. But if you go to the if you go to the southern hemisphere, everything gets flipped around. So unfortunately, the book's pictures are backwards. In a northern latitude, you can see the path of the celestial equator here is traveling through the southern sky. But if you go to a southern latitude, then the celestial equator travels through your northern sky. So what I said, Ava, is if the sun is in the southern sky, you know that you're in the northern hemisphere. But if the sun were instead in the northern hemisphere, you'd know that you were actually in the southern hemisphere, right? Our sun, for a person in Rhode Island, the sun travels through the southern sky. But a person in Argentina or somewhere in the southern hemisphere, they would see the sun travel through the northern sky. It's very simple. Sun is in the south, you were in the north. That's it. 25 degrees north. How are you going to find your longitude?
Oh, you're going to do 2200 minus 12 because that's where the sun's at.
Yeah, how did you know the local time was 12 o'clock? That's very good. How did you know this?
Because up is 12.
The sun is
down is 6.
The sun is on your meridian, and the sun is on your meridian when it's at the highest in the sky. Very good, Andy. So that's minus 12. So how many hours is that?
10.
10. That'd be 10.
Okay, so how do I convert that into a longitude? Well, how do I go from hours to degrees?
Wait, you times it by your 25, so it'd be.
Nope.
Is it 15 degrees per hour?
Always. It is always 15 degrees per hour. I know why you said 25 because you thought the 15 degrees per hour was related to the 15 degrees north in the sample problem, Andrew. But that's not the case. They were just coincidentally the same number. It's always 15 degrees per hour. So what's my longitude? Don't think about this too hard, guys.
150 west, 150 degrees west.
How do you know it's west? How did you know it was west and not 150 east?
Because the sun is at the on the south. I don't know.
No. East and west have nothing to do with north and south. It's about your relationship to the prime meridian. The universal time tells you the time in Greenwich, England. Is England, Joel might know, is England ahead of us or behind us, Joel, in Rhode Island?
It's ahead of us because it's east of us.
Right. So when you're west
And
of England,
England is ground zero.
right. So I always think of it as this. If it's later in England, you're in the west. If it's earlier in England, you're in the east. Since 22 is later than 12, this observer is west. Ava, I gave you the universal time as 2200 hours. The real question that you should have asked Ava is, how do I know the ship is at 12 noon? The reason you know that the ship is at 12 noon is because the sun is on your meridian at 12 noon. So when the sun is on your meridian, it's always noon o'clock, and noon is 1200 hours. The reason you subtract them is because you want to find your hours away from England first. Then you can convert it to degrees from England. Okay.
So what is it that you said? If it's later in England, it's what?
If England is later than you, then you are west. If England is earlier than you, then you are east.
Okay.
Ready for the next problem, guys? Okay.
You're really boring Fenway. He's snoring.
Huh? Oh, Fenway is
You're
snoring.
boring my dog. He's snoring.
Well, I guess we could do a problem called Catch the Bone, but I don't know if that's going to help you on the test. Okay. Guys, I'm trying to take on some of the hardest problems first while your mind is sharpest. You want to take on a local sidereal time problem? Because those are always hard. Local sidereal time. Here's a hint. You're going to need this formula for some of it. The hour angle is the local sidereal time minus the right ascension. You should have that in your formula sheet. There is a famous star called Arcturus. Arcturus has a right ascension of 14 hours and 15 minutes. The given is that Arcturus is on your western horizon. One, find the hour angle of Arcturus. 2, find the local sidereal time. 3, this is a challenge question. This is the hard one. which point will cross your meridian next? Your options are A, the spring equinox, B, summer solstice, C, fall equinox, D, winter solstice. Okay, I'm gonna give you a hint. Can you guess what the hint is? What's the hint?
Draw a
Effing
diagram.
diagram. That's right. Draw a diagram. But how do we draw these diagrams? The diagram looks like the Lost at Sea one, but it's a little different in one important respect. All right, take a few moments to just work on it. I'm not going to tell you any more yet. You can ask me if you're stumped. Okay, at this point, if you know what you're doing, you should have drawn a diagram. Can anyone tell me what the diagram looks like?
That's what I was doing. That's what I was doing.
Do you know, Andrew, what the diagram's supposed to look like?
Yeah, so you're gonna have east on the left side and west on the right.
Very good. That's very important.
And you're gonna have the meridian in the middle.
The meridian, but yes, exactly.
The meridian.
Okay. So Andy, this is your diagram, but you need one more thing. The given,
Yeah,
where is Arcturus going to be on this diagram?
Arcturus
is a star, and I've given you the givens that it's on your western horizon. So where should I put the star?
The west.
Oh, to the west.
Whereabouts? All of this is west. I'm going to put a blue star wherever Arcturus is. Tell me where to put blue. Tell me exactly where.
A little
What
bit.
did you say what the coordinates were? What was it? I know it was west, but
bottom right corner, probably. Like
bottom right.
Like here?
Should be like right there.
Exactly.
Yeah, because that's the horizon.
That's the horizon, exactly. It's on your western horizon. The star's right there. Now, if the star is there, you should know the hour angle already. You should be able to answer number one just based off the definition of hour angle. I guess we'd better read the definition of hour angle, hadn't we? What's the definition of hour angle?
it's the time since the meridian.
Okay. So what do you think then? How does that help me?
Is it 6 hours or?
Very good. Who got that? Who are
Noah?
you? Noah.
Noah.
Oh, hi. Noah, you smarty pants. Will you explain that to everyone, how you figured out that it was 6 hours?
Well, I just thought of it like it's gonna take
Which way does the sky rotate, Noah?
from east to west.
Right. So it's going in that direction, right?
Yeah,
And the meridian is here, right, Noah?
yeah.
So how did you know
And
from here to there was 6 hours?
I figured it took 12 hours for it to go across the whole sky, and that's half of that.
Very good. It's 24 hours around the circle, and a quarter of a circle is 6 hours. Excellent. Noah has gotten question 1 correct. What about question 2, Noah? How are you going to do that one since you're so smart?
You just have to do, you just rearrange that equation a little bit. So you have LST equals,
I don't want to mess this up, so. Okay. So how do I solve for LST?
you just have to add the hour angle and the, is it right ascension? Is that what it's called?
Yes. That is correct, Noah. So I guess we'd better add these up, right? The hour angle is 6 hours. And the right ascension is 1415. What does that give us?
20 hours and 15 minutes.
Very good. Now the challenge question, up to now, question 1 and question 2 were supposed to be easy, or easier anyways. Question 3 is the hard question. To answer this question, you should first start off by knowing what is the definition of local sidereal time. Why doesn't someone like Noah read us the definition of local sidereal time while I eat a pickle chip?
It's the hour angle of the spring equinox.
In that case, that should tell you where on the sky the spring equinox is. Where is the spring equinox? Hint, you may have to use the bottom part of the sky as well.
It's going to be in like the bottom left quadrant, kind of.
0, 6, 12, 18.
Oh, you start at 0 for the meridian?
Always. Our angle is time since meridian, not time since something else. So do you want to revise your answer about where the spring equinox is, Noah? I want to put
Yeah,
it.
it's in the top. It's in the top left.
How far
It's
up?
going to be like a third of the way up, about.
So what's the answer to part 3?
A.
Spring equinox.
Let's make sure. Where's the fall equinox?
It's going to be like on the exact opposite.
Very good, Noah. Okay, Noah, here's the real trick. Is this summer or is that summer? Everything goes eastward along the
I'd say bottom.
Yep. This is summer and that's winter. Because the ecliptic always runs eastward. The sun goes east in an east direction over the course of the year. That's a very tricky one. So make sure you remember that, okay? Okay, guys, you did pretty good, actually. I'm honestly impressed. Shall we move on to a different type of question? Because there's many other types of questions that you'll have to solve.
Yes.
This will at least give you a fighting chance, okay? Okay, let's see what else I got in my magic tricks. It's time for a little Newtonian mechanics. let's calculate the period of a geosynchronous satellite. There's a famous geosynchronous satellite. Its name is Satcom. And Satcom has a mass of only 40 kilograms. So it doesn't weigh much more than, or much less than you. It has an orbital altitude of 36,580 kilometers. We also need to know the mass of the Earth, 6 times 10 to the 24 kilograms. And the radius of the Earth is 6,400 kilometers. Obviously, guys, the hint for this problem is going to be the same as the hint for all the other problems. What's the hint?
Draw a diagram.
Draw an effing diagram. However, last 2 problems, it took you guys like 5 or 10 minutes just to figure out what the diagram was. I don't feel like waiting that long, so I'm going to show you what the diagram is, but you'd better write it down as well. Here's the diagram that you want. You have the Earth. This is the radius of Earth and the mass of Earth. You guys will remember we did this in our labs together last week, right? So this is a test to see if you remember what we did. Okay, question 1. Find the period of Satcom. Question 2. Find the force of gravity between Earth and Satcom. By the way, BTW means between, not by the way, or here. Okay. 3. Find escape velocity from Satcom's orbit. It's going to be different than the escape velocity of Earth. Okay, 3 questions. You know what to do. Give it a whack. Give you a few extra minutes for this one. By the way, if you need a hint, we did this in one of our, or we did some of this in one of our labs. A note to night students and students watching later, I'm going to be pausing the recording while the students work on the problem. That way I don't fill up the recording with dead air. You might want to pause and work on this for 5 minutes before continuing the video. Hold on a second, Andrew. Let's resume the recording. You guys want to talk about it? See how far we got?
Yeah.
Okay, Andrew, what'd you do?
So I found 6,400 kilometers for RE.
Okay, that's a given. You didn't find it. It was given to you.
No, it was given.
What formula should we use for number 1? Did you guys figure out the formula?
It's the one where you get like the period squared equals 4 pi squared over, or times
Newton's version of Kepler's third law.
That's
yeah,
right.
that one.
Or what I call NK3.
Yeah.
4 pi squared a cubed over g times the sum of the masses. M1 plus M2. All right, so what do you do? I'm stumped. I don't know what to do. I'm lost. Where's my damn marker?
Wouldn't you have to find A?
Okay, Bella. How do I find A?
I'm going with what we did on one of our labs, so I might be wrong, but
All right.
I'm gonna assume it's the RE plus what was it? The 36,580 kilometers.
That's
I
right.
might be wrong. Oh, it's right.
That's absolutely right. So what does that give you?
42,980 kilometers.
Did I do that right?
Well, I can't see from here, but I'm assuming yes. There you
You
go.
gotta move your little window. You know, guys, when you can't see the bottom, you can move the little people boxes around. I think if you grab them and
Not on ours.
Oh, you
We
can't?
can pin you. No, because it's the angle of your camera, not ours.
Oh, shoot. Did I just remove? Oh, never mind. Sorry.
No, you're fine.
I wanted to give you guys permission to do things. I wish they would just give everyone permission to do everything. Okay, I'm sorry. Well, I see what you're saying. Okay, I don't know what the shit to do here.
No,
Okay.
it's fine now.
Okay, fine. All right, so what do I do next, Bella?
Then
I'm just sitting down so I can not block the board. I want to look and engage with you guys, but then I block the board. So I'm just going to float over here. What do I do next?
Sure.
You have to make A into meters.
Very good, Noah. Noah, can you help me do that like a pro?
Yeah. It's times the division bar, and then you have kilometers on the bottom and meters on top. It's going to be 1,000 meters for every kilometer.
And when you plug it in, what do you get?
You want like the big number or scientific notation?
Is the number bigger than 1,000,000?
Yeah.
Then scientific notation is probably best.
So I'll say like 4.3 times 10 to the 6 or 10 to the 7.
Oh, yes. 1, 2, 3, 4, 5, 6, 7. Or we could make it 43 times 10 to the 6, right?
Yeah.
That's probably a classy way to do it. Okay. Noah, Bella, I'm impressed. You guys are doing it all right. Now what do I do?
You just got to plug everything into that equation.
What am I going to use for M1 plus M2?
Just use the mass of Earth.
Yeah, you can ignore the mass of the Satcom, right? That's an addition, so you can ignore Satcom. And just make this the mass of Earth. Okay. Do you guys have the questions written down? Because at this point, to set it up, I'm going to have to erase everything. I'll just assume that's yes. I just need to make some space up here. Okay, so to find the period is the big square root of 4 times pi squared times 43 million meters cubed divided by big G times the mass of Earth. What do you get?
86,000.
Give me 3 sig figs.
86,400.
What are the units? Nicely done.
It's going to be seconds, but you have to convert it to years, I think.
In this case, can I recommend converting it to hours instead?
Yeah, that's easier for me.
All right, how do I do that?
Oh, you got the seconds. I was about to say that.
That's okay. Noah's killing it today. What about my units here? Hey.
Oh, you want me to do it?
Well, I don't know.
Seconds
Maybe
to minutes.
Seconds
Pardon?
at bottom.
You go
Yep.
seconds on the bottom and minutes on the top.
Okay.
Then then minutes on the bottom, hours on top.
Oh,
Now
I
give me
know
some
the numbers.
conversions.
So 60 on the bottom, 1 on top. Then 60 on the bottom and 1 on top.
And what do you get?
Hold on, I didn't do it yet. I got 24
24 what?
hours.
Huh. That's interesting. I guess that's why they call it a Geo Synchronous Satellite. A geosynchronous satellite has the same orbit as the spin of Earth. And therefore, as Earth spins, the satellite will stay in the exact same position, hovering over the ground, and you can bounce your cell phone tower off that, and you can do communications with it because it'll stay hovering over the same point, say in Mexico City or in Rhode Island or something. You guys are impressing me today. You're actually doing pretty decent all on your own, and I like your moves. You guys ready for another problem?
As long as it's
Harder
not
ones.
this,
Pardon?
as long as it's not this kind.
Well, there are a couple more like this that we probably should try, Jake. Okay. Get ready for this one.
Wait, weren't we supposed to find the force of gravity and the escape velocity?
Fuck yeah. Okay, we should do those, Jake. Thank you. I'm sorry, I forgot. How do I find the force of gravity?
G times mass of Earth times mass of satellite divided by a squared, which is 43 times 10 to the 6.
Okay, you guys want to plug in the numbers? What do you get? Big G is 7 times 10 to the minus 11. The mass of Earth is 6 times 10 to the 24. Mass of Satcom is 40 kilograms. Plug and chug. Gabby, what you get?
I'm still writing it down. I haven't plugged it in.
Okay, well, finish up and let me know what you get. Did you guys want to see me write it out all formally? Does that help you? How do I help you? I kind of did a
I
way.
would do.
I did a lame up here. Do you guys want me to do it better?
Um,
I'm gonna pause. Okay,
Yeah.
Jake, what'd you get?
I got 9.08, so 9.1.
9.1 what?
Newtons? I don't know.
Yeah.
Oh, really?
It's Newtons. That's right. It's approximately the same force of gravity as this exerts when I hold it in my hands. Nice. How about the escape velocity?
Hava, when I typed it in, I didn't use the parentheses. I just did the bottom and then I just hit the square button on the calculator.
That's right. I'll show you what to do, but I'm going to go fast. Wait. Shoot, I need more light.
Yeah, no problem. I think I remember he said that before. It just helps me to not type it in.
Yeah, you don't use the parentheses. All right, there we go. All right. 7 exp minus 11 times 6 exp 24 times 40 divided by 43 million square key equals. How about your escape velocity? You guys have to move faster or we're not going to cover all the problems because we only have a half an hour left and there's so many more problems to do. So you guys, I want you to kind of a little more fortissimo, a little less allegrando. You know what I'm saying?
$4,400.
Units?
Is it going to be meters per second
Very good.
or kilometers per?
It's meters per second because that's MKS. How many kilometers per second is that?
4.4.
Good. All right, those are pretty easy. Those are relatively straightforward once you get that far. Okay, I need to erase this so we can move on to the next problem. We really got to push here. I want you to get exposure to all of the problems. Okay, here's a new problem. The planet Mercury has a synodic period of 116 days. Find the sidereal period of Mercury. 2. Find the average distance from Sun to Mercury. 3. Convert number 1 to seconds. 4. Convert number 2 to meters. 5. Find the mass of the sun. I'll give you a few minutes for that. But we can't take too long, so just 5 minutes. All right, let's talk about it. How do I find the sidereal period?
P sin over P sin plus 1 year.
The sidereal period is P sin over P sin plus 1 year. Okay. Parentheses are not optional. So what'd you get?
$2.035.
Sorry, say that again.
2.035
What are your units?
years.
No. Wow, I bet I know what you did.
Did you convert, Jake?
No, of course he
No.
didn't. Nor did he use parentheses. He did a double bad. Jake, this formula requires particular units. Days is not the right unit. You're going to have to convert to years first. Jake, help me do that as punishment.
Well, so you times by a division bar,
Yeah.
and you put days on the bottom and years on the top.
Right.
So I think it's 365 on the bottom and 1 on top.
Okay. What do you end up with?
Something wrong.
Well, what's the right?
I got 0.3.
Huh?
I got 0.31, which doesn't make sense.
Why doesn't it make sense? The period of Mercury is less than a year.
That would be right.
Could you give me it as 3 or 4 sig figs?
0.317 or 0.32.
That I want 3 sig figs.
0.318.
Yeah, Jake, you're
Instead of
not
4
rounding well. Jake, if you were going to
Instead of
round
4
it to
sig
sig
fig is-
figs, that
is
should have been
8.
0.3. Do
It's
good rounding.
0.3178, right, Jake?
Yeah.
Yeah, so it should be
Okay,
0.31.
now plug into that formula, this time using parentheses, Jake, and tell me what your sidereal period is. Well,
.241
units,
days.
no,
Oh, we switch back to years.
Years.
it's all in years. How do I do question 2? How do I do question 2, students? The average distance from Sun to Mercury.
You do, because Earth goes around the sun once a year. So you do 1 AU times 0.24, but you convert the 1 AU to 150
No,
million kilometers.
no. I don't remember there being a law that says P equals A. That's not how that shit works. Just because Mercury's a quarter of a year does not mean it's a quarter of an AU. That don't make no sense.
So the p squared equals a cubed.
That's right. The relationship goes like this. P squared equals a cubed. So try that one out. What's the P, Joel?
0.24.
Yeah, 0.24 years. It's the sidereal period. I'm going to try an experiment after the exam. I'm going to calculate the average test score by humans who participate with me and share video. And I'm going to calculate the average score of people who don't share video. And I suspect I'm going to see a remarkable difference between those two scores. We'll see. All right, so what's the answer then?
Yep, 0.39.
Pardon?
0.39.
0.24 squared. Yeah.
Then the cube root.
0.39 what?
AU.
Excellent. Okay, now you convert 1 to seconds and convert 2 to meters. I'm going to give you guys a very useful conversion factor here. 1 year is equal to 3.15 times 10 to the 7 seconds. If you remember that for your exam, that will greatly speed things up. So what is 0.24 years? That gives me 7.56 million seconds.
Wait, I'm confused how you got, so how did you get the 0.39?
By doing p squared equals a cubed. A is the cube root of p squared, right? So I did 0.24. First I square it, then I cube root it, shift cube root, and I get 0.39. Okay, so how many seconds? Oh, I calculated them for you. How many meters is 0.39 AU? All right, I don't have time to wait for you guys to do it because you're too slow. 5.9 times 10 to the 10 meters. And then, in theory, we're going to move on to another problem because you guys are moving too slowly, unfortunately. But the mass of the sun would be found through Newton's version of Kepler's third law. You do 4 times pi squared times a cubed over gp squared. You've got your a here, and you've got your p there. You're going to have to work that one out by yourself on the exam because I want to do one more question with you before 3 o'clock. Okay? Okay, I'm going to erase this in a moment.
Give me 1 second, please.
Mm-hmm.
Okay, I'm back.
All right, there's a problem that I want to try with you guys that I know is going to be real challenging for you, and it kind of uses some of this stuff. All right. The diagram I'm going to actually show you how to draw it because I have a feeling if I left it up to you, you wouldn't get it right the first time. This problem is one that we've talked about many times in class. It's how to get the mass of Jupiter from observations. And we're going to take observations of Jupiter and its moon Io, just like Galileo did. So just like Galileo, we're observing from Earth, and we're observing the planet Jupiter separated from some angle from its moon Io. And I'm going to tell you that the angular separation is 145 arc seconds. I'm also going to tell you that Jupiter has a synodic period of 1.092 years. I'm going to tell you that Io has a period of 42 hours around Jupiter. Here's what I want you to do. 1, convert the angular separation from arc seconds to degrees. That's just dimensional analysis on 145 arc seconds. 2, convert the period of Io to seconds. That's NOR dimensional analysis. 3, find the sidereal period of Jupiter. 4, find the distance between the Sun and Jupiter. 5, subtract 1 AU from that to get the distance from Earth. Here are the key problems. 6, find the separation between Jupiter and Io. And then 7, find the mass of Jupiter. That's going to take you a little bit. Get started on it, see what you can do. Please, if you're stumped, ask me for a hint. Night students, I'm going to pause and you should work on this for a moment yourself. Okay, guys, why don't you talk to me and tell me what's going on? How far do we get? Did anyone actually get to these questions? Did any single person get to these 2 questions?
I'm on 6 right now.
Oh, cool. Anybody besides Joel? Damn.
But I'm struggling with.
Well, ask me some questions. Let's pretend this was the test. What are your questions? I can't really help you unless you're willing to ask for it. Everything here makes sense to me, so I don't have any questions for myself.
Okay, so if I use I have all the information, I just don't know how to.
What's the answer to number 1, Cam? I'm going to pick on random people. Cam, what's the answer to number 1? Cam, you don't know? You couldn't even do number 1.
Wait, is this being
I'm looking for my
recorded?
book.
Well, you don't, Cam, you don't even need your book. Number 1 is a unit. Cam, do you know how to do dimensional analysis?
I mean,
Well, the answer is yes or no.
sorta.
Well, you don't need your book to do dimensional analysis. You just need the steps of dimensional analysis. You can look them up in your notes. What's the first step of dimensional analysis?
The first step. I just nice. The first step is to write down the number to convert with its units.
So what do I want to write down then?
42 hours.
That's not what I asked you to convert. I asked you to convert the angular separation from arc seconds to degrees. What do I mean by that? What is the angular separation between Io and Jupiter? You know what I mean by angle, right?
Yeah.
That's an angle.
Yeah.
What's the fucking angle?
145 degrees.
Try again. Those units are not degrees.
Oh, 145 degree inches?
Nope, those aren't. I know those are the symbol for inches for some people, but
It's arc seconds.
Arc seconds.
Okay.
That symbol, Cam, means arc seconds.
Okay.
That's what I'm trying to get you to convert. It's a unit conversion from units of arc seconds to degrees. So if the first step of dimensional analysis is to write down the number to convert with its units, what should I write down?
145 arc seconds.
What's step 2?
You multiply
by a division bar. What's step 3?
You put the units in first. Put the units in first, and then you cancel. But I think the units you need is
arc seconds at the bottom and degrees on the top.
Do you know a conversion from arc seconds to degrees? Wait, was that Juan that I heard there?
Yep. No, I don't.
Juan, then you
Yes.
can't go from arc seconds to degrees. What are you gonna? Why don't you look at your formula sheet? What do you have on your formula sheet? Where's that bloody formula sheet? What do you see here in your conversion factors in the formula sheet? Wow. Guys, I'm scared. This is dimensional analysis. I want you to be able to do this.
One arc minute equals 60 arc seconds.
Well, okay, so Joel, are you suggesting?
So if you change that dimensional analysis, you put arc minutes on top.
Yeah, you got to go to arc minutes first.
So one would be on top, 60 on bottom.
Okay.
Times another dimensional or division bar.
Right.
One degree on top and 60 arc minutes on bottom.
Yeah. That's all I wanted you to do, Cam, was just dimensional analysis. Convert from seconds to degrees. So what do you get?
I'm still learning.
That's okay, but you've got to learn this, Cam, okay? That's critical. Cam,
I'm a
from
little
now
nervous
on-
about the exam.
From now on, Cam, you're doing every single dimensional analysis conversion I have to do. Do you understand? Every single time it's going to be you from now on. All right. What does this turn out to be?
So 145.
Divide by 60, divide by 60 again.
Okay, I gotta get more light. 45 divided. Oh, 145 divided by 60 divided by 60. I got 0.04
Units?
degrees.
Fine. Okay. Convert period of EO to seconds. Guess whose job that is, Cam?
Mine.
That's a you job, yeah. So can you help me convert the period of EO to seconds? What's your first step of dimensional analysis?
Of course, to write down the number to convert.
With
So I think that
units.
42 hours.
Okay. I'm gonna erase this. Okay. Then what?
So then you multiply it by a division bar.
Okay. Then what?
So you're gonna have hours. You're gonna have the units on each side. So hours beyond, below, and I think seconds on top.
Do you know the number of seconds in an hour?
60.
No,
False.
Oh wait.
it's supposed to be minutes on top.
Oh yeah, that's right.
That's okay. You might have known.
Yeah, I was thinking 60 seconds per minute. That's come thrown off.
Right, right.
So it'll be 60 minutes per hour.
Okay. How about the next one?
Minutes below and seconds on top. So it'll be 60 seconds in a minute.
Punch them up. Tell them what you get.
Okay, so 42.
I got it by observing EO in my telescope, Ava. Ava, 42 hours was a given. I got that from looking through my telescope at the moon and watching it orbit around Jupiter.
I got 151,200
Units?
seconds.
Fine. Okay. Next up, find the sidereal period of Jupiter. How am I going to do that?
So you write down the number to convert with the units. So
That's not a conversion factor. You actually have to use a formula for number 3.
oh, okay.
How do I find a sidereal period knowing that the synodic period is 1.092 years?
So you divide. Oh wait, do you divide?
We need a formula. Look at your formula sheet.
No, it's just to find the SID. It's the synodic divided by
Is Jupiter, hold on. Can we slow down, Bella? Is Jupiter an outer planet or an inner planet?
outer.
Hell yeah. So that's the formula you want right there, right?
Yes.
Okay. Let's punch them up.
Time.
What do you get? That's a U job. What do you get?
So 1 point. I got 0, but I don't know if I'm doing the calculation correctly.
Are you using parentheses? I already know the answer to that question. No, you're not. So no,
I'm
you're
not.
doing it correctly. Those parentheses, I didn't just put them there for my health. They're there because you need them. If you don't use the parentheses, you will of course get it wrong. So plug it in and use the parentheses.
Okay. 0.92 divided.
Open parentheses, dot, 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 close parentheses equal.
Okay.
It's okay. I'm trying to play bad cop now, and I'm doing a really good job at it because I'm grumpy.
11.86 or 11.87.
Let's just call it 11.9 years.
All right.
Okay, here comes a tricky one. How do I find the distance between Jupiter and Saturn if I know the sidereal, not Saturn. How do I find the distance between the Sun to Jupiter if I know its sidereal period is 11.9 years? We did this in the previous problem. How did you find the distance between the Sun to Mercury? What was the formula that you used?
It was p sub divided by p sub plus 1 year, or no, minus 1 year.
No, that was to convert from synodic to sidereal period. Now I want to find the distance between Jupiter and the Sun. I'm trying to find this distance here. How do I get this distance? It's got something to do with the sidereal period in question 3. There's a hint.
Okay.
Anyone in the class know? I'm not just talking to Cam now.
A squared equals a cubed.
That's right. For number 4, you're going to use.
I got that one wrong on the last.
You always have to use p squared. Never forget about p squared equals a cubed. Okay, you've got the period. Find me the distance. How do I do it?
11.9 squared, and then take the cube root to get a.
A is the cube root of 11.9 squared. What's that give us?
Okay.
5.2 AU.
What do you get if you subtract 1 AU?
You get 4.2 AU.
Very good. Okay. Now comes the time for the big moment. Question 6 and question 7. I'm going to need to erase in order to solve for question 6 and question 7. So I'm going to erase now. Okay. How do I find the separation? Well, I know the distance up here is 4.2 AU. What I'm going to do is I'm going to use the small angle formula to solve for S, the separation between Jupiter and Io. So I have S is theta times D times 2 pi over 360 degrees. But I'll probably need to convert 4.2 AU to kilometers first. So 4.2 AU times AUs into kilometers. 1 AU is 150 million kilometers. S will equal 0.04 degrees. What's 150 times 4? 600, right?
It's 63 times 10 to the 7.
Okay. 630 million kilometers then.
Okay, you can go down with you.
Times 2 pi over 360 degrees. What do you get?
Why'd you change the distance?
Well, I don't want to measure the distance between the moon and Jupiter in AU because
All right, yeah.
whatever units you put in for D are the same units you get for S. So I decided I'd better convert into kilometers first. That'll be a trick, Noah, on the test. See, I'm thinking to do this because I'm experienced enough that I know where this is going and I know what to think about next. I'm already on the next step and I'm thinking, I don't want the distance between Jupiter and Io and AU. I want it in kilometers. And eventually I'm going to want it in meters, okay?
Right.
So I get 440,000 meters is what I get. Sorry, kilometers. Is that right? It's 40. Yeah, it's close. How many meters is that, Noah?
440 million.
Yeah. Okay, here's the trick. What was S in the small angle formula is now going to become A in Newton's version of Kepler's third law. So to find the mass of Jupiter, we'll have the mass of Jupiter is equal to 4 pi squared A cubed over GP squared. So that becomes 4 times pi squared 440 million meters cubed over big G times, what was it, 151,000 seconds squared?
151, 200, but yeah.
What was it?
Yeah, it was 151, 200.
Well, all right, 151 is fine.
But yeah.
Okay. 4 times pi squared times 440 exp6 cubed divided by 7, next 11 divided by 151,000. I get 2 times 10 to the 27 kilograms, which is the correct answer. That was sure a hell of a problem, but you're going to do something just like that on the test.
On the test, are you going to be looking at just the answer, or are you going to have to like look through all of our steps?
Noah, you don't have to show your work on the test, but do you know why I've trained you to show the work? So that you can follow what you're doing. You may find in the test, if you know exactly what you're doing and you can do it without showing the work, then fine, do that. But if you're getting messed up, you might want to do the work out slow and careful and neat to make sure you're getting the right answer. Also, if you ask me for a hint, I'm not going to be able to help you if you're just like, I got it wrong. If instead you're like, I'm doing this and it's not coming out right, I can say, ooh, did you make sure to change your units from AU to kilometers? I can, if you show your work, I can give you a better hint, you know?
Right.
Brendan?
Yeah.
Can you angle the camera down so I can just make sure I have the numbers?
There are other problems that are going to be on the test, but unfortunately, that's all we have time for today. You guys are still growing, but you need to get better at dimensional analysis. You need to get very fast at dimensional analysis, right, Cam?
Yes.
All right. Well, God knows this went on long enough. I did as many problems as I could, guys, and we actually did do quite a few problems. let's think about it. All of those are problems that you're going to have to do on the test. Now you have a vague idea of how to go about it. You have a memory and a record of doing it. So that should help you out come test time, right? I will also be there to give you tips and help. All right. Well, class, I'll see you Monday for the exam. Reach out if you get in a pickle, okay? Good luck. I'll be around for help during the exam. So let's all log in. I'll send a Zoom as normal a little before 11:30, okay? Okay, over and out.
And then, Brendan,
Yep.
what time are you doing the Zoom thing tonight?
Oh yeah, I need to do a Zoom tonight at 6. I forgot to send out an email for that. So I'm going to send out the email now, 6 p.m. for the night class. Ava, Joel, you're in the night class. You might want to log back in so we can talk about it.
Oh yeah.
If you're
I'll
willing.
be there. See you in a couple hours.
I'm just going to talk to you guys about night class specific issues, about how I can help you guys, whether or not we want to like have me log in for the exam. Okay, Ava, if you have an appointment, you don't have to be there. I'd say just come during the day to take your test, okay? But yeah, if you want to pop in, you're always welcome. I want to be able to talk to the night students since I don't get to talk to them as much. Hell, I don't get to talk to most of the day students because you're all damn trolls. But anyways, I'll see you guys on Monday, okay? Over and out.